All right, so you run your regression. Now it's time to check your assumptions again. All right, so this is going to be what we call residual analysis. And here are the steps that we're going to be doing. We're going to be computing our residuals and our predicted values and checking a lot of different scatter plots and histograms to see if we still are meeting our line assumptions that we talked about earlier. All right, so just a review of what we checked for before the regression. We looked at our histograms, our scatter plots, and our box plots for the independent and dependent variables. After the regression, we're mainly going to be focusing on those residuals, which you can just remember the residuals are the error terms, the actual values minus the predicted values. Okay, so here's it organized by plot, and then here's it organized by assumption. So what is residual analysis? Basically, it says we're going to take all of those error terms and put them on a plot versus what the predicted values were. So if you look at this plot, this is the independent variable versus the dependent variable, and the residual versus the fitted value. These red dots here are highlighted so you can see how this translates into the residual plot, right? So basically, if this line turns into this line here, then you can see that same scatter around the fit line is going to be visible in the residual plot. What we're looking for when we get these residual plots is we're looking for a nice, even scatter, right, in general, and not some of the issues that I'm going to show you coming up next, right? So this is a pretty ideal residual plot right here. All right, so our first assumption is linearity, right? And we already saw in our checking before the assumptions how our scatter plot could look non-linear, right? You can see the same thing when you do these residual versus predicted plots. You can see the scatter that kind of forms a curve instead of a straight line. So that would give you some indication that your data is not linear and not meeting that assumption. Next is the independence assumption, right? And remember that that assumption is that the errors are statistically independent from each other. The residuals don't give any information about each other. And there's three types of lack of independence: correlated observations, correlated predictors, and missing variables. So we already went over the first two. So we're gonna go over those again, and now looking at how you see them in residual plots. So the first one, correlated observations. So we talked about how you can look at your independent and dependent variable scatter plots to see whether it might be that some variables are related to, some observations are going to be related to each other. What you can do with your residuals is actually plot them based on when they were collected, right? So this is time versus the residual, again, those error terms, right? And what you can see here is that the data that was collected at the very beginning and the very end are going to be higher. Those errors are higher than the errors for the data that's collected kind of in the middle of the time frame. And there could be a lot of reasons that this is happening, right? Maybe this is where your research assistants were really good with the protocol, and then they started to slack off more and get a little sloppy, and then they got retrained, and so they started to do the protocol a little bit better, right? But that's a problem, right? And this can reveal that, and you really need to see that, okay, there's something about how much error each data point has that's related to when that point was collected, and that is something you're going to have to address in your analysis. The second form of lack of independence we can have is when your predictors are correlated to each other. Now you can see this before you run the regression by looking at the bivariate correlations or your t-tests or your ANOVAs, but you can also look at it after regression with this statistic called the variance inflation factor. I'm not going to talk about how it's calculated, but you can see it over here in SPSS, and in Stata you just type VIF and it shows up. And it's going to give you a number between 0 and infinity. It's going to tell you how much are these variables collectively related to each other. Now, an interesting thing about these correlated predictors, or multicollinearity is what we're talking about, is that you can have two variables that are very closely related, but not necessarily be a problem. But you can have two variables that aren't necessarily related to each other, but once you put them in an equation with a whole bunch of other variables, then they suddenly become a problem, right? So they collectively they collectively become a problem. What you do to check for that is you're looking for a BIF of over 10, right? So all of these are pretty good. If there was something that was like a 10 or 14 or 17, then we'd have to look at these variables and say, oh, do we really need all of these in the regression? Is there something that we should be concerned about in what they're measuring or how they were measured, and think about what is the most important thing to keep in our analysis. Then the third type of independence is where you have missing variables, right? So you can only check for this after your regression, and you run it as a scatter plot of those residuals, the error terms, against independent variables that you didn't include in your model. So this is a regression where the dependent variable was blood pressure, right? And what they did is they said, okay, we're going to not have weight in the model, but maybe we should have included it. So what you do is you just look at weight as the independent variable, and then the residual, the error terms, as the dependent variable. And what you can see, instead of that nice even scatter, we actually see a positive relationship between the error terms and weight. So this would suggest that there's something about how much you weigh that is predicting how well that model or blood pressure predicted, how well predicted the data, right? So how close your fitted value was to your actual value is dependent on how much you weigh, right? So that the people who weigh more, their error terms are a lot larger than the people who kind of weigh more in this middle area here, right? So this would suggest that you need to add weight into your model. You can do this kind of analysis with any potential independent variable, so there's really an unlimited number of variables that you can potentially include. But again, just like when we're talking about other control variables, you want to think about what's logical, what's common in your field, to do this kind of post-analysis to check for missing variables. And then of course, it also depends on what you actually have in your data set. If they hadn't measured weight, then there's no way they would have known that weight should have been in their model. So that's independence. Our next assumption is normality, and this is the same one. Our errors should be normally distributed. After the regression, you can check this by looking at the residual versus the predicted values plot, right? This is where you're looking for that even scatter, but you can also see outliers, right, on this type of plot. And then the next plot that we're going to talk about is called a normal probability plot. And this, you're just looking for those dots to hug the line, right? So this is a normal probability plot. What this is doing is saying if each value was where it should be perfectly on a normal curve, right, then it would fall along this line. And so any dots that are not falling along the line are kind of deviating from that perfect normal curve. So you can use this to see whether your data is normal to begin with, and you can also see whether there are outliers in here. So here, there's that outlier, kind of just way off what the normal curve should be. So you can use the normal probability plot to detect both sort of how nice and normally curved your data is, and also whether you have any outliers. And then our last assumption is equal variance. So remember, this is where the variance in the dependent variable is similar across all levels of the predictor, right? And so here's a scatter plot of your independent variable versus your dependent variable. And here you can see how that variance gets wider. The spread of the line of the data gets wider as you go further out on your x-axis. You can also see this in your residual plots, right? So you can do your residual versus your predicted values. You can do it in residuals versus independent variables, right? To see if you have some scatter that looks like it's widening from one end to another. All right, so let me go back to by plot. So actually when you're running these plots, right, when you look at the residuals histogram, you can check for multiple things, normality and outliers. And when you're running these multiple residual versus predicted value plots, you can check for a lot of things at one time. So in class, we're going to practice going over this. I just want to point out that you can look at one plot and really diagnose a whole bunch of issues. So here is an example of some residual plots. So all these plots are residual versus predicted values. In this one, we've got a nice even scatter. So this is where we will say there's no issues here. The assumptions are pretty good, right? Over here, what we would see is we have that lack of equal variance, right? The residuals are, the spread of the residuals is much smaller on this end compared to this end. Here, we can see that non-linearity, right? Where residuals are forming some curves. And here, not only do we have non-linearity, we also have that spread being smaller on this end of the curve compared to that other end of the curve. So here's an example of how you can have multiple issues just in one residual plot. All right, and here is a test for yourself, right? So I want you to write down what issues you notice in each of these residual plots.